Morning, sir.
Morning. Morning. Okay, Assalamualaikum and good morning everyone. So today we will before we go to next lecture, next topic, I want to discuss on maybe give some clue on assignment 4. Okay, so assignment 4, in developing a vision prosthesis for restoration of vision to the blind, a hexagonal array of platinum disc electrodes is being considered to electrically stimulate the surface of the inner retina from within the vitreous humor. Dia je lah. Okay, the electrode disc are 0.3 millimeter. So each electrode, so the circle here are electrodes. So has diameter 0.3 millimeter with center spacing 1 millimeter. So the spacing between them is 1 millimeter. The geometry for a twin hex electrode setup is shown below. So this 7 arrangement here is one hex, and this is another hex. For a domain of dimension 6 times 6 times 0.2 millimeter. Okay, the square dimension is this one, with electrodes located on the upper surface. Okay, so the electrodes are on the upper surface. The interior of the domain consists of vitreous fluid with electrical conductivity of 1 Siemens per meter. The lower surface corresponds to the inner retina layer. A DC current of 1 milliampere is injected in the center electrode of left hex. Okay, so left hex, we call it hex 1. So we put 1 milliampere in the center, and various DC current magnitudes are injected in the center electrode of right hex, hex 2. So in the center here, we apply various current. All other electrodes, or we call it guards, are at ground potential, and all other boundaries are electrically insulated. Okay, so the question, solve the model using computational mathematics by doing the following: build the prosthesis geometry and set the boundary conditions and solve the model, and then analyze the model, simulate this system for currents injected in hex 2. So we have current in hex 2 from 0.2, 0.4, 0.6, 0.8 and 1.0. So here use parametric solver. So I will show you how to use parametric solver. And then calculate the current density in hex 1 and hex 2. Calculate the percentage difference and then plot the percentage difference against current density in hex 2. Okay, so I have drawn the geometry. So geometry tu pandai-pandai lukis lah, okay. Ni pun lama juga nak lukis. Okay, so I have the geometry ready. So let's go to question 2 here, set the physics. Okay, so firstly, we choose electric current EC here from your multi-physics selection just now. Memang tak lah. Okay, step dia ni je. Simple je, 2 je.
Workplane tu, sir. Buka workplane tu, sir.
Oh, tak boleh. Dia tak boleh tekan tau. Tak tahu kenapa. Dia tak ada benda pun lah, macam ni je. Dia banyak copy je, copy, move.
So yang bulat-bulat tu dia lubang ke dia bulat je?
Dia bulat dekat surface
Dia
dekat
bukan,
atas ni.
dia bukan hollow ke?
Bukan. Dia macam electrode je.
Oh.
Uh, kena lukis ni lah. Tapi sebenarnya tak kisah pun. Susunan dia maybe tak center ke tak apa. Yang penting bulatan ni tersusun macam kehendak soalan 1 meter apart, okay? 1 millimeter apart between them. So kalau kata when you guys draw, maybe it's slightly upper, maybe not in the middle, not in the center, that's fine. As long as the distance between them is correct, okay? Okay, so firstly, the question said that the plate has current conductivity, electrical conductivity equals 1. So you just select current conservation and put 1 here. Okay, meaning that all the domain here has electrical conductivity equals 1. And then the question also said that at center hex 1 here has current density 1 milliampere. So here you can either put 1 milliampere or you can calculate the area here, but I put 1 milliampere here. And then on hex 2, the center electrode has various current. So to run parametric sweep, as what question asks, parametric solver, what you need to do is you define a variable on the current here. For example, I define I hex 2. And then when you define something here, you go to global global definition parameters 1 and put I hex 2. And in the expression, you can put any numbers. So here I put 0 milliampere per meter squared. So to run parametric sweep, you need to define a parameter in the global definition. And in the expression, you can put any number, but with the correct unit, okay? Make sure that the unit is the same as the unit you want to use. Here, ampere per meter square. But because we use milliampere, so milliampere per meter square. So to define unit in expression, you need to put the square bracket here, and then put the unit inside the square bracket. Okay, then the other electrodes are the guards or the ground. So you define ground. From the electric current, you right click, you choose ground and choose the other electrodes. Okay, so the other settings are zero flux Newman boundary condition. So this is basically by default. So you don't need to set anything here. Electrically insulated zero flux Newman boundary condition is by default. It should be this electric insulation here. So when you set everything, and when you see at the electric insulation, then the boundary that you have set will have the tag overridden here. So overridden here means that it's already override using other settings like normal current density or ground. So you don't need to set anything in the electric insulation. It will be by default. Okay, so that's the physics part. And I question analyze the model. First, simulate the system for current injected in hex 2 from 0.2 until 1.0, increment 0.2. So use parametric solver. So you go to your study. So first thing you need to do is right click study 1 and choose parametric sweep. And then in the parametric sweep, in the parameter name here, you click plus and choose the parameter that you want to varies. Okay, you want to vary. So here the parameter that you want to vary is the current in the center hex 2, which is I hex 2. So in the parameter value list, you can write all the value required by the question. So it starts from 0.2, 0.4, 0.6, 0.8, 1.0. You can write like this, but you must have spaces in between the values. Or you can also write in terms of range. So range starts from 0.2, increase by 0.2 until 1.0. You have two ways to write the values. After you set like this, then you can start computing. So the purpose of parametric sweep, basically in console, when you have simulation that requires you to run many times, but you need to vary only a few parameters or only one parameter, for example. So the console allows you to use parametric sweep and give the parameter values the values that you want to run, and you only need to open one console only. So instead of you run 5 different simulations, so in console you can only run one simulation, but it will automatically change the value of current here. For example, current here. So tak payah buka banyak konsol, mungkin lambat ke ataupun menyebabkan banyak RAM nak buka konsol. Okay, so when you have when the computation has finished, then you can go to second question. Okay, so if you see the plot here, the electric potential, then you can play around with the data. So first you need to change to study 1 parametric solutions here. So from here you can change your parameter I hex 2. For example, if you want to see the results for 0.2, sama je, tak berubah pun. Yang berubah dia punya apa ni? The range of values here. Okay. Okay, another thing that you can use in console is to calculate something. For example, here calculate the current density in hex 1 and hex 2. Okay, how to calculate the current density? So firstly is that you can go to here, derive values here. You can right click and Sekejap Okay, so you can go to derive values here, right click, and then you can choose, for example, average. So because the electrode is in the form of surface, so in the 2D surface, okay? So you cannot determine one single value in the surface, meaning that you need to find maybe average value or maybe the maximum value in the surface, okay? Because it has a lot of values in there. So here I use average, so choose surface average and select surface hex 1 here, the center hex 1, and also center hex 2. Okay, so here meaning that you want to calculate the average in surface hex 1 and hex 2. And then the question say calculate the current density. So here, when you want to calculate the current density, you go to expression and you can add expression here. Press the add expression and you can try to find where is the current density. So you can either type current density. So there are a lot of current densities here. Displacement current density, external current, induced current, current density in X, Y, Z component. So here the current density that the question wants is the normal current density. I think this is the magnitude of the current density. So you just click, double click, and then you click evaluate. Okay, so this is the the current density of hex 1. So to calculate the current density for hex 2, you need to repeat the process, okay? So duplicate. Okay, so you get the current density for hex 2 and current density for hex 1. Okay, so question number 2, calculate the percentage difference ni. You can do the same thing in derived values. Macam mana buat? Okay, so question yang calculate ni rasanya tak boleh pakai console, kena kira di luar console, okay? Meaning that you take this value, maybe import into MATLAB ke, and then you calculate the percentage difference, okay? So when you calculate the percentage difference, and then you can plot the percentage difference against the current density. Okay, so the important things that I want to show here is how to use parametric sweep. So when you want to use parametric sweep, you must have the parameter that you want to vary, and then define the parameter in global definition parameters. And then in the parametric sweep, you put the range of value, and then you can compute. Okay, that's one thing. And then another thing is how to use derived values. So when you want to calculate something, you can go to derived values and right click and choose whatever calculation that you want. Okay, for example here, to calculate current density in the electrode surface. So because it's a surface, so it has a lot of points, surface average, because we want to get only one single value. Okay, so hopefully you can continue do the assignment number 4. Okay.
Doktor, nak submit kena macam yang minggu lepas punya
Yes, save in Word document, submit in Kalam.
Baik, terima kasih.
Okay, so let's continue with our lectures. Okay, so last week we have learned about Maxwell equation, how to use Maxwell equation, and why some simulation requires Maxwell equation. For example, we want to model electrical current flowing from defibrillator. So those who have a project title related to electrical, I think FES, functional electrical stimulation, and also transcranial electrical apa entah. So those two projects basically will use what we have learned last week. Okay, so the concept is similar to the assignment or the tutorial. You need to define the location of electrodes and apply some currents, and then maybe from there you can evaluate how much is the current, the density ke. Maybe you can plot streamline, for example. So that's I think should be enough for those who do topic related to electrical. Okay, so for today we will go into learning how to do simulation related to solid mechanics. Okay, so biosolid mechanics. So for today, students will be able to understand the steps involved in solving computational model using FM software, and then solve and analyze various applications of solid mechanics model in biomechanical engineering application. So so before we go to tutorial, let me briefly tell you about what is biosolid mechanics. So in biology, in mechanics of biology, we call it biomechanics. Okay, so we have two types of biomechanics. First is solid mechanics, and second is fluid mechanics. So solid mechanics basically deals with deformation of solid under applied loads or pressure or force. And since our body is constantly being applied with loads, when you walk, you apply load to your bones or to your feet, to your leg, and our heart is constantly beating. So our heart also is a solid, so it has loads applied to it. Okay, constantly apply. And then we have muscle. Our muscle, when we lift heavy object, for example, so we use our muscle to lift the loads. So we can simulate this by using solid mechanics. Okay, and in solid mechanics, that you have learned, SOM 1, SOM 2, maybe you are familiar with engineering stress, for example, engineering stress, through stress, engineering strain, through strain, and you maybe have learned how to calculate this stress and strain. But to use this stress and strain directly on our body is not really accurate because it doesn't represent the true stress or strain of our body. Because our body, if you look at the muscle itself, it has a specific shape like a spindle, macam bentuk apa panggil benda tu, tak tahu nak cakap. Okay, so the muscle has stress and strain distribution differently in the muscle. Okay, meaning that if you apply load on the muscle, there will be stress and strain distribution. So what you have learned so far in SOM 1 and SOM 2, basically you assume that the geometry has what we call it isotropic value of stress and strain. So to allow for calculation of distribution of stress and strain, we have a different theory. We call it solid continuum mechanics. Okay, so basically continuum mechanics study the behavior, mechanical behavior of materials as a continuous mass rather than discrete particles. So basically it uses fundamental law of physics such as conservation of mass, momentum, and energy. Okay, kita tak belajar lah detail on this theory, okay? So because we are using continuum mechanics, so in COMSOL or in the theory itself, you have to use tensor, okay? The concept of tensor. So tensor basically is a matrix, but it's not a small matrix like you have learned 3 by 3 or 2 by 2. Or if you still remember your finite element class, we have stiffness tensor when you want to calculate the displacement of springs, for example. So the stiffness tensor besar kan, ada sometimes 6 by 6, 8 by 8 matrix. So here we also have tensor for the solid mechanics, but we don't only have one first order, second order tensor. We also have maybe third order tensor. Third order maksudnya dia dah bentuk box lah matrix tu. So your matrix, your regular matrix is in the form of 2D, okay? X and Y, ada X and Y axis. But for third order or fourth order, dia dah bentuk cube, okay? Ada X, Y, Z. So fourth order dia ada X, Y, Z dengan satu lagi dimension. So all of these are in the theory of continuum mechanics. Okay, ni boleh. Okay, ni basically in the continuum mechanics, we have two state that we can use to define the mechanics of a solid. So we can refer the mechanics of the solid using reference state or from the undeformed point of view, and we can also use current state from deformed point of view. Maksud point of view ni maksudnya kalau pernah dengar teori Einstein relativity, pernah baca ke atau pernah tengok YouTube ke. So when we look at one object, if you look from a point, a car moving, then you either say, maybe you will say that the car is moving very fast. But if you are in the car, driving the car, maybe you didn't feel pun yang the car is going very fast because you are moving with the car. So there are two point of view here. So the first point of view is you are sitting stationarily on a point and looking at the car. So you can see the car moving very fast. But if you sit in the car, then you might think that the car is not moving that fast. Maybe laju tapi tak laju sangat. Tapi kawan you yang duduk luar kereta nampak kereta tu gerak laju. So ada dua point of view kat sini. So ada dua state. So one of the state we call it undeformed state, and the other state is deformed state. So benda ni if you do FYP related to solid mechanics, maybe penting sebenarnya. Okay. So stress, we have force over area. So just now I mentioned about the tensor. So stress tensor has 9 components in the stress. In one stress, we have 9 components or 9 values arranged in matrix. Okay. So the stress is not uniformly distributed. So it has a different value at different location. For example, in this box, we have different value of stress at different location. So we cannot represent the stress with one single value. We need to use stress tensor in the form of matrix. Okay, boleh skip. Okay, so kalau berminat boleh baca dekat nota ni, tapi tak keluar exam. So subjek continuum mechanics ni sebenarnya dia sangat luas lah. So tak boleh ajar dalam one lecture, dia kena satu sem. Okay, so the important things in biosolid mechanics is that our body, our tissue has different we call constitutive law of materials. Maksudnya badan kita juga ada material properties, ada constitutive law dia. So far in SOM 1 and SOM 2 you have learned about linear elastic. So linear elastic, basically you say that the stress is linearly dependent with strain. Okay, maksudnya stress sama dengan some constant times the strain. So the constant may be Young modulus and Poisson ratio. So that's a linear elastic. But our body, for example muscle or skin, we cannot use linear elastic because ada beberapa sebab. Okay, nanti kita akan tengok. So we usually use hyperelastic law and viscoelastic law. So in this lecture we only focus on hyperelastic. Okay, so viscoelastic ni case lain. Okay. Okay, so a little bit overview of the stress strain curve. So if you still remember rubber, so rubber has hyperelastic material properties. So rubber has this kind of curve. Okay, not rubber je, ni yang regular punya curve. Okay, but rubber has when you apply stress, then the strain will be very large. Okay, so small stress applied on a rubber will produce very large strain or deformation. So kalau ada getah sekarang, kalau you apply stress, sikit je tarik, then getah tu terus memanjang. Tapi when you release the stress, then the getah, the rubber will go back to its original shape. So same with our tissue, our body tissue, muscle, skin, our heart. For example, muscle lah. So when we lift an object and we release the object, then the muscle will go to its original shape. So kalau muscle tak boleh go to original shape, then tangan kita akan jadi kejang lah, terlekat macam ni. Okay, so kita cut something, lepaskan, then it will go to original shape. You can release the pressure on the muscle. So basically what I want to say here is that our body tissue have been modeled using hyperelastic model. So basically they assume that our body is having similar properties as rubber. So other example of hyperelastic materials other than rubbers are skin, our aorta, our muscle. Okay, so there are in finite element software, there are many hyperelastic materials already built in the software. Okay, for example, neo-Hookean, Moni-Rivlin, Ogden, and you can also write your own code by using user-defined. But usually we use Moni-Rivlin and neo-Hookean because this is simple to use. Okay, if you want to write your own code, ni mungkin project master PhD ataupun FYP. So Moni Rivlin ni, ni saya selalu cerita entah kenapa. So Moni Rivlin ni adalah orang yang bertanggungjawab buat material properties for rubber. So dia yang derive equation for material properties of rubbers. So Moni Rivlin ni masa dia nak buat eksperimen on rubbers, dia guna getah dekat Malaysia masa zaman penjajahan British dulu tiba kan. So British bawa benih getah dari Brazil kan. So dari Brazil diorang tanam dekat Malaysia, dan Moni Rivlin ni guna getah-getah yang ada dekat Malaysia untuk buat eksperimen on to derive the hyperelastic material for rubbers. So they call the material properties or the equation as Moni Rivlin. So persoalan dia dekat sini ialah kenapa tiba-tiba cerita pasal rubber Malaysia ialah adakah Moni Rivlin ni dia acknowledge pasal Malaysia dah lah jajah negara kita, atau guna getah kita pula. Adakah dia orang acknowledge dalam paper dia ke atau dalam buku dia ke getah yang diambil adalah dari Malaysia macam tu. So kita boleh saman dia kot. Okay, ni tak ada kaitan. Okay, so there are the important things in this lecture is that our body has different material properties than the regular one. So the one that you have learned in SOM 1 and SOM 2 is linear elastic. So our body has mostly has hyperelastic material model. Okay, so let's do the tutorial. So you can turn on your console and let's learn how to apply hyperelastic model on console. Okay, so this tutorial basically wants to apply force on a simple cube geometry that has Moni-Rivlin material properties. Okay, so the question says simulate the myocardial shear experiment below in console using Moni-Rivlin constitutive law with material parameters C1 10 kilopascal and C2 2 kilopascal. Density equals 1000 kilogram per meter cube. Assume the myocardial sample is a cube, dimension 3 by 3 by 3 millimeter. Okay, so when you apply the stress, the pressure, you will get something like this, the results. Okay, these are the steps. Okay, so firstly, select 3 dimension. So start, select 3 dimension. Okay, ini step console lama punya 4.2 rasanya. So slightly different, okay. And in select console multiphysics, choose structural mechanics module. So structural mechanics. And then choose solid. So solid mechanics here. Okay, go next. And then stationary. So it says here use parametric analysis. So parametric analysis sama macam lecture 5 hari tu. Kita buat dalam stationary, okay? Okay, so after that, we can start by drawing the geometry. So right click block. So the dimension is 3 millimeter. So 3 millimeter. And at corner 0, 0, 0. And then build all. Okay, this is your object, your geometry. Okay. Then physics setting. Select subdomain 1. Set the material model to hyperelastic. Okay, so basically apa yang dicakap ialah dia nak buat material properties dia hyperelastic. So in solid mechanics here, by default, basically apa yang dicakap ialah dia nak buat material properties dia hyperelastic. So in solid mechanics here, by default, it will give you linear elastic material. So we don't want to use linear elastic, we want to use hyperelastic. So you go to solid mechanics, you can either go to physics on top. No. Okay, you can go here. Tapi saya tak prefer yang atas ni. Saya prefer right click. So you right click solid mechanics. When you right click, you go to material models and choose hyperelastic. Okay. Okay, when you choose hyperelastic, then first what you need to do is you need to select the domain. So here in domain selection here, just click the cube. Okay, so you choose subdomain 1 here. And then under the hyperelastic model, select monirivlin. So here, under hyperelastic material, so we have material model here. So I said just now we have a lot of material model. So if you open the drop down here, there are many material models exist. Okay, already built in console. Okay, so by default it will give you neo-Hookean. So here we want to use monirivlin. So just now the question gives you monirivlin with two parameters C1 and C2. So we choose monirivlin 2 parameters. Okay, because it has C1 and C2 only. Okay, so in the parameter, we can insert the value of C1 and C2. So C1 is 1e power 4 and C2 is 2e power 3. And then change the density to 1000. Okay. Then we need to set the boundary conditions. Okay, so the boundary condition basically what we are going to set is that we are setting a stress on top and fix the bottom. So the first thing that we need to do is fix the bottom. So right click solid mechanics and choose fix constraint here. Okay, so choose fix constraint and select the bottom boundary. So we fix the boundary at the bottom here. And then we want to apply a shear stress on top. So we use prescribed displacement. So right click again and choose prescribed displacement. And choose the top boundary. And then check the Rx checkbox and set the displacement in the x direction as D shear. Check the Ry and Rz and leave displacement at 0. So basically what you need to do is press the check button here. Ry and Rz, meaning that the displacement in y and z direction, so you put 0 by default. But in the x direction, you define D shear. So because we want to use parametric sweep, so we define a parameter here, D shear, and we also define on global definition parameters 1 here. So define D shear and put any value here. So you can put the unit as well. Okay, so in mesh, use coarse. So element size here, you can change to coarse. Okay, so coarser, okay? So coarser, build all. And then specify the parameters in parametric solver. So in study 1, right click, choose parametric sweep, and add the parameter D shear. And then specify the range of parameters. So from 0 with step size 1e minus 4. So 1e minus 4 until 0.0015. Okay, so here another step to calculate because you want to plot the force. Here the force against shear, the graph force against shear. So you need to calculate the force. So here you can go to component definition here. Right click and choose integration coupling. Integration. And then choose surface integration. Choose the top surface. And then in definition, you define a variable. So you want to use the integration here. So in variable, you define a parameter, a variable force. Then you integrate the solid stress. So solid dot s x code. Okay, solid dot sx. This is the stress in x direction. Okay, so when you integrate the stress in x direction over area, so you get the force. Okay, because stress is force over area. Okay, so you integrate stress over area, so you get the force. Okay, so after you do the calculation, then you can go to study 1 and compute. Mesti ada error. Okay, tahu error dia. Okay, dekat sini letak je dekat bug modulus 1e10. Okay. Okay, so the reason we use coarse mesh just now sebab simulation dia lama gila tadi. So 40 saat, okay, 1 minit. So that's why kita guna coarse, okay. Kita nak cepat sikit. koas pun 40 saat. Kalau normal tadi maybe 2 minit lah kot, 3 minit. Okay, so after you solve the model, then default plot is the von Mises stress. So to get the plot same as the example given, so the example given here is plot apa ni, tak nampak. So total displacement, okay. So to plot total displacement, you can go to stress solid here, drop down, and here the expression is for solid masses. So you can change the plot and find displacement. So this displacement is here, solid displacement, okay. Double click and plot, okay. Dapat macam dalam result tadi. Okay, so after you plot, then we want to plot the graph, okay. So the graph is basically force against the shear. So you can go to results, right click and choose 1D plot. And in 1D plot, you can right click again and choose global code. Okay, so in the expression, you can find the force that you have defined earlier. So I think it's here in definition, variables, force, okay, right click. And then x-axis data, we plot against the parameter value, which is the D shear. Okay, you right click. Terbalik pula. So terbalik kita letak je negatif depan. Okay, it should be the same. Lebih kurang lah. Okay. So we get some results here. Okay, so in the plot you can do a lot of things. For example, you can put title. So title, for example, force. You can name it force, and then when you plot, keluar force kat sini. Okay, sama macam MATLAB juga. Okay, you can play around anything in the plot, and you can also plot other things that you want. Okay, you can play around. Okay, so that's all for today's tutorial. So ada assignment macam biasalah, assignment 5. Okay, so assignment 5 ni test 2 sem lepas punya. Okay, last semester test question. Okay, so the question is inside your book. So dalam buku muka surat so in the book page 301, this question, the left ventricle in the heart here, and jawapan dia pun ada dekat belakang. Okay, kalau pergi kat belakang ada jawapan. Jawapan dia tak adalah lengkap, dia just bagi tahu nak tekan apa je. Ni jawapan dia. So jawapan dia macam bagi tahu generally what are the steps involved. So try to follow the steps and try to use your kebijaksanaan juga untuk jawab soalan tadi. Okay, so the question is the same. So here you use 2 parameters, Monin-Rivlin. So some mistakes here. So ada satu benda silap kat sini. So here it's not 5 kilopascal, 5000, it's 5 kilopascal. And then yang plot ni kena explore lah macam mana nak plot. Yang question C ni dalam buku dia ada ajar macam nak buat. Okay, so that's it for today's class. And assignment ni hantar macam biasa hari Ahad minggu depan. Okay, so that's it for today. Thank you for coming. Assalamualaikum and goodbye.
Ya, sir.
Okay.
Yang assignment 4 tu, kan kita kan kena buat graph. So, guna MATLAB. Contoh guna MATLAB.
Macam tu lah.
Jadi, nak hantar file MATLAB.
Buat macam ni kot. Nanti dapat MATLAB akan dapat graph. Maybe print screen graph ke, save JPG ke. Ambil graph tu letak dalam Word document yang untuk simulation console tu. Sebab simulation console tu akan save dalam Word, so letak je paste gambar tu dalam Word document.
Faham. Terima kasih.
Okay, so bye-bye. Thank you. Ada soalan boleh tanya. Bye-bye. Assalamualaikum.
Waalaikumsalam, sir. Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Terima kasih, sir.
Thank
Bye.
you. Bye. Pukul apa meeting?
Sebelah ya.
Sebelah saya. Okay. Boleh.